Thank you for coming to my dissertation defense. My project is the development of soft robotic hand orthoses, or exoskeletons, to help with recovery from stroke and other neurological impairments. And it takes the unconventional approach of first identifying and then verifying a problem through customer discovery, and then developing a technological solution, the process of human-centered design. First, I will explain the background and original idea, detail the customer discovery process and revelations, and then describe the design, testing, and analysis of 2 hand orthoses for neuro patients. Finally, I will conclude with a success summary and recommendations for future work. First, I'll give you some background on the project. Close to 1 million people experience neurological events every year in the US, and about 350,000 of these result in upper limb impairment. Stroke accounts for roughly 3/4 of these, but other demographics such as Parkinson's, ALS, spinal cord injury, multiple sclerosis, etc. are also affected. During the neurological event, a part of the brain either dies if it's a stroke or otherwise loses connection to the rest of the body for other disorders. Depending on the part of the brain and body affected, the lack of hand control, including difficulties grasping and opening and instability. This is a debilitating, life-changing event that leaves patients dependent on others for even the most basic tasks. Over time, their struggles compound, resulting in fatigue, frustration, and a host of additional problems. To help mitigate these issues, many patients receive assistive devices such as splints, but current technology is inadequate. The standard passive devices come in limited sizes and either prevent motion or constrain the hand to move unnaturally by coupling wrist motion to finger motion. A few powered orthoses exist on the market for at-home use, but these tend to be large, bulky, and expensive. Furthermore, many devices are difficult to put on, or are uncomfortable or abrasive due to rigidity, further deterring patients and even some providers from use. These quotes elaborating on the issues are from people active in the field, and I'll explain more about that later in the presentation. In the last couple of decades, soft robotic exoskeletons have been developed for both rehabilitation and assistance in order to enable more natural motion and combat the issues caused by the rigidity of existing technology. A few have been developed for therapeutic purposes, more for assistive purposes, and a couple fulfill both. Although these devices solve the rigidity issues of existing products, they are still difficult to put on, and many are weak and ineffective. One thing you may notice about them is that they all look the same. So why make another one? Well, ours look different. But also, we decided to take the unconventional approach of first talking to patients, caregivers, and providers to see what they need. We discovered that there are 2 primary ways stroke manifests itself in upper limb impairment. One is spastic, where the hands are stiff and clenched, and one is flaccid, where the hands are completely limp. So 2 different populations need to be served. However, they share the common issue of not being able to voluntarily move their fingers, so any device with individual finger slots is out. Based on the patient needs we discovered, we realized we need a different device for each demographic. 2 powered hand orthoses, a stretching orthosis to mitigate contractures for patients with spastic hands, and a grasping orthosis to provide assistance to flaccid patients. By developing rehabilitative devices to help neuro patients regain their hand function, we hope to improve their quality of life and reduce hands-on time for caregivers and therapists. In order to find funding for this project and let patient needs guide product design, the customer discovery journey began with participation in Vanderbilt's Ideator program through the Wondery. This solidified the need for a powered hand orthosis and prompted participation in the National Science Foundation's I-Corps program. For any of you not familiar, I-Corps is like a research version of Shark Tank. Dr. Barth and Sean Glinter, an industry mentor, participated in I-Corps with me as a team, and we finished in 2nd place, earning a $50,000 grant. I'll show you the trailer for the project as an introduction, and then get into the details on what we learned and how that guided the project. I'm Elissa Ledoux, a mechanical engineer and entrepreneurial lead on I-Corps Team 2237 OrthoHand. We're developing a powered hand orthosis to help stroke survivors and other neuro patients regain and maintain their independence and reduce hands-on time for caregivers and therapists.
My name is Eric Barth. I'm a professor of mechanical engineering at Vanderbilt University. My research area is in the modeling and control of dynamic systems with applications in fluid-powered medical devices and soft robotics.
Hi, this is Sean Blinter, 2237 IM for OrthoHand. I have over 25 years of licensing technologies and commercializing them.
After my grandmother had a stroke and lost some of her manual dexterity, I wanted to put my skills as a robot clone designer to work, develop a similar technology to help humans. At first, I thought all stroke survivors were like my grandma, struggling with fine motor skills. But after just a few interviews, I realized that many had a more basic need.
When I had my stroke, my whole life changed. I can't curl my hair no more. Can't look at the kitchen with my hands. Your arm, it's all even when I feel old, sore after, move my elbow, this tension and let it just turn up. My fingernails digging in my palm. They current so hard it makes me bleed. Open my fingers no more even.
About 80 interviews in, we realized that other neurological disorders, such as MS and ALS, share similar characteristics of weakness, spasticity, and loss of coordination. After expanding our customer discovery network, we realized that ALS may be our best entry point into the market because it is a small patient population with a demonstrated severe need and significant opportunities to receive funding for durable medical equipment. Based on what we learned from customer discovery in the iCode program, we're expanding our target market and simplifying our device functionality in order to meet the more basic needs of neuro patients. Now I will talk about the hand orthosis ecosystem and patient demographics. Our original hypothesis was that stroke survivors need help with fine and gross motor skills, and that current hand orthotics are inadequate. In order to test this hypothesis, we conversed with patients, caregivers, and acute and chronic care providers, doctors, nurses, and physical and occupational therapists. Focusing our dialogue in these parts of the ecosystem allowed us to connect directly to the people most intimately familiar with the challenges that neuro patients face. Patients and caregivers provided personal perspectives based on individual experiences, while doctors, nurses, and physical and occupational therapists shared information that is common knowledge to the medical community, but unfamiliar in the engineering domain. This is how we realized that patients fell into two populations depending on their upper limb impairment: spastic or toned with stiff clenched hands, and flaccid with limp hands. I conversed with 164 different people, some of them multiple times. Stroke was by far the largest category since it is the most abundant and the one that we started with. We then expanded this interviewing to other patient demographics, including multiple sclerosis, Parkinson's, and ALS. After learning that these patients share similar characteristics of weakness, spasticity, and loss of coordination. You can see the different types of providers on the top and patients on the bottom of the chart. Of about 800,000 stroke victims in the US annually, most survive. After completing rehab, 40% of these have mild to severe impairment, our target population. Strokes can be either ischemic due to a clot or hemorrhagic due to a bleed. And these patients often die, while a clot is a lot more common. While most people who have strokes are older, like age 50 plus, younger people can have them due to congenital defects, birth control because of clotting factors, or drug use because of blood pressure spikes. Strokes cause unilateral impairment, and the extent of recovery is based on the severity and location of the stroke, as well as external factors such as intervention, patient activity, and access to therapy and assistive devices. An occupational therapist at Neurotherapy Nashville said the earlier the intervention, the better to prevent hand spasticity and contractures. So just as a disclaimer here, all of the names have been changed from our conversations in order to protect personal privacy. Patients have severe physical needs, which I'll explain first, but less obvious effects of neurological impairment include psychological and financial struggles, exacerbating the need for affordable solutions. We found that many stroke survivors have more basic needs than we originally anticipated. While the specifics of each neurological condition vary, upper limb problems are the most common, and virtually all the patients share similar characteristics of weakness, spasticity, and loss of coordination. One of my friends is a hospital dietitian, and she explained how this loss of hand function affects the patient's abilities to eat and communicate. Because things are so busy in a hospital, the patient's nutritional consumption is often overlooked, which snowballs into an increasingly negative effect on their recovery. Spasticity is a tightness or stiffness of the muscles, caused by both contractive brain signals and shrinking muscles and tendons. Because of this, many people struggle simply to open their hands. Over time, the hand can involuntarily clench harder and harder into a fist, which leads to complications such as bleeding, contractures, and further loss of function, leaving the patient dependent on others for even the most basic tasks. TJ, a stroke survivor and autobiographical author, told us of his continued battle with hand spasticity. And a stroke caregiver mentioned how hard it is to even perform basic hygiene on a patient with a contractured hand. People try to combat this by stuffing a washcloth or a ball into the patient's fist, or strapping their hand to a paddle brace. But while these prevent the hand from contracting further, they do not improve functionality. Therapists agree that there must be a better solution. A physical therapist emphasized that patients need early access to the right devices, and an occupational therapist said a stretching device would be a major contribution. So our device functionalities should include both therapeutic and gross motor assistive. For anyone with stiffness, stretching is so important. Sometimes the patient is too weak or stiff to stretch on their own, or lacks motivation, and the caregiver or therapist must guide them through the range of motion. This is essential for spastic patients to maintain flexibility and prevent contractures. And flaccid patients also need to move their muscles to retrain the mind and body connection. Patients and providers told us things like, keep the hand limber, keep things moving, and high reps helps with neuroplasticity. Despite a contracture, patients still struggle with instability in the affected limb and often drop items suddenly. While stroke survivors complain the most about spasticity, ALS patients mention weakness as their biggest obstacle, and multiple sclerosis patients almost universally mention dropping things. The lack of sensory feedback in the hand can also lead to unintentionally crushing objects. Overcoming the lost or deteriorating mind-body connection can be overwhelming and frustrating. Patients would like to be able to use the affected hand as a supporting member for bimanual tasks. Ginger, a stroke survivor and avid baker, wishes she could hold the mixing bowl with her affected hand while she scrapes it with her unaffected one. And Ken, a stroke survivor and Second Amendment enthusiast, longs to be able to reload his guns with ammunition. Losing the use of one or both hands means patients struggle with all activities of daily living: feeding, dressing, toileting, and so on. They universally complain that everything takes twice as long, if not longer, than before their condition onset, if they can even do these things at all. This affects everything patients do every day, leaving them dependent on a caregiver. Pete, an ALS patient, explained that as his muscles degenerate, he can no longer even get out of bed or off of the toilet without help. And Gerald, a stroke survivor, explained that since his impairment is unilateral, he cannot do any bimanual tasks on his own. One of my former students helped her grandmother care for an uncle who had a stroke while she was in high school. She explained the difficulties of small, weaker women caring for large men. Patients' loss of physical independence affects their social and emotional health and their whole identity. The psychological impacts of this dependence consist of frustration, depression, cognitive impairment, and left side neglect. Many patients grow frustrated trying over and over to do tasks they used to be able to perform with ease. My grandmother Mona explained that for her, this was the hardest part. And Gemma, another stroke survivor, described how her physical disabilities led to depression. Cognitive impairment is also a big deal, as many patients can have trouble understanding instructions, communicating, or remembering things. And Sydney, a physical therapist, explained a condition stroke survivors experience called left side neglect, in which the brain actually forgets the affected body part even exists, so patients must be reminded to use it. And unfortunately, many patients, caregivers, and even some providers are not well informed about these neurological conditions. Regarding post-stroke recovery, there are two schools of thought: rehabilitate or compensate. Rehabilitate means to get the affected body part back functioning how it was before, or at least some semblance of that. Whereas compensate means to use the other body part to compensate for what the affected one can no longer do. The older a patient is, the less likely they are to be encouraged to recover and instead expected to simply accept their condition. Some providers are legitimately ignorant, while others are simply lazy. I was surprised by the number of doctors I spoke with who said things like, "I just write a prescription for whatever the therapist tells me," or therapists who said, "No, I don't think we brace those types of patients, but I don't know why." Financial obstacles come in the form of insurance hurdles and lost income. Providers ranted about how insurance is a major obstacle to getting assistive devices into the hands of patients, even though the sooner they can receive medical equipment, the better. However, some diagnoses such as ALS and MS have foundations that provide some financial support. Because patients' conditions are so debilitating, they're often unable to work, and many times their spouse must also stop working in order to become a full-time caregiver. This means they struggle to afford therapy and medical equipment. So if affairs are so dismal, how can patients regain or maintain their independence and quality of life? There are 4 key areas: physical, mental and spiritual, emotional and social, and resources. Exercise and stretching have the most direct impact on patients' physical conditions. Amy, a stroke caregiver and certified medical assistant, explained that the brain will try to reconnect to the body if it sees a need to. Several patients attributed their success to consistent practice of rehabilitation. Reed Thomas, the band director at MTSU, had a stroke a few years ago that could have spelled the end of his career. He described doing hand exercises for conductors nonstop in his hospital bed, and 3 semesters later was fully back in action. TJ, a football coach, single dad, and author of a book about his stroke experience and recovery, explained how the need to be there for his kids motivated his daily drive, but the struggle never fully goes away. However, as one stroke caregiver explained, the patients who try the hardest succeed the most. The Holy Trinity contributing to the mental and spiritual aspects of recovery consists of cognition, positivity, and faith. Patients emphasize the importance of setting an achievable goal every day, comparing performance today to performance post-event rather than pre-event, and trusting that God has a plan. However, maintaining a positive mental outlook can be a struggle, and an assistive device could provide peace of mind in knowing that there's a tangible solution to their problems. Support systems and social involvement are also critical factors in recovery, and many patients cite their community or support group involvement as ways to avoid depression and motivate each other. Several stroke survivors wrote books to share their stories and recovery tips pictured above. The caregivers are also highly motivated for patients to recover and see an assistive device as a way to both help their loved ones and save time for themselves, while word of their successes will spread through their social media and support groups. Finally, one of the most necessary but hardest to obtain aspects of recovery is resources, therapy, and assistive devices. Caregivers and providers would love to give the best equipment to every patient, but the problem comes with financial obstacles, necessitating affordable technology. Dan, a stroke survivor and technology enthusiast who has found and tested a wealth of equipment on his own, said he pours any extra money he has into this, but acknowledges that many patients cannot do that. The cheaper a device is, the more patients could obtain it and benefit from it. So to recap, we had 3 major pivots based on our customer discovery. First, the simplified functionality from fine to gross motor assistive in the form of therapeutic cycle stretching for spastic patients and power grasp assist for flaccid patients. Second, the change in device structure from hard to soft robotics. And finally, expanding our potential customer base from stroke to include other neurologically impaired populations. Given the abundance of problems that neuropatients face, and the factors contributing to recovery that could be augmented by an assistive device, hand orthoses are a much-needed solution. However, the devices must actually meet patients' needs in order to be beneficial. So here's a set of design requirements derived from the customer discovery insights. Since many neuropatients can't voluntarily move their fingers, ease of donning is essential for them to be able to wear an orthosis. A patient must be able to put the orthosis on his or her affected hand using the unaffected hand and without the assistance of a caregiver. Ideally, this would take less than 1 minute. Dynamic flexibility is another important quality. Problems with existing technology include rigidly constraining the hand to move around unnatural axes, limited sizing, and bulky and uncomfortable apparatus. Since many neurologically impaired patients suffer from reduced sensation in their affected limb, preventing abrasion and therefore infection is important, necessitating a switch to soft robotics. For the patients who can feel, the device must be comfortable or they will not want to wear it. Finally, eliminating rigid constraints enables more natural motion because the joints in the hand can rotate around axes that are biomechanically appropriate rather than externally imposed. The ideal performance metric to meet in terms of range of motion of the human hand is 250 degrees of flexion. As previously established, spastic patients need to stretch to prevent contractures, and flaccid patients need to move their muscles to retrain the mind-body connection. To alleviate the cognitive and physical burdens of constantly moving their hands, and because many patients lack voluntary control, the orthosis should open and close to cyclically stretch the affected hand. If the patient cannot move on his or her own, the caregiver or therapist must move their muscles for them. Especially for those patients, an orthosis would reduce the interaction required by the caregiver and enable therapy to happen constantly if desired. Furthermore, it would capitalize on the brain's neuroplasticity by increasing the amount of therapy in a daily timeframe. Due to the extreme weakness that flaccid neuropatients face, a hand orthosis for that demographic should provide an assistive function as well, the ability to lock into place for power grasps. Remember Gemma, who wanted to scrape her mixing bowl, and Ken, who wanted to load ammunition, but other patients want to do manual tasks too. So with the orthosis, the affected hand would hold an object stable, while a more dexterous motion is performed with the unaffected hand. Grip force should be between 40 to 60 newtons to match the capabilities of the human hand for activities of daily living. 25 to 38 newtons would be on par with the strongest research prototypes that exist currently, although as low as 15 newtons would exceed the abilities of several prototypes. Controlling the device must be easy for patients who lack voluntary motion with that hand and often suffer from mental impairment as well. The control scheme must have two qualities: easy to command behavior and able to regulate grasping force in order to not drop or crush objects. So it should include power and trigger buttons that are easy to press with the unaffected hand or another body part, and sensors to regulate grip force. Due to the gamut of financial troubles inflicting patients, including lost income and insurance resistance, affordability is critical for getting devices into the hands of patients. Ideally, an orthosis would be cheap enough that a patient or caregiver could purchase it easily. A couple of interviewees mentioned $500 as an amount they would consider paying, although we shot for a goal of $1,000 for our prototyping in order to put the market cost in an affordable ballpark. A cheaper device could also be more favorable to insurance, especially if it is shown to be effective. The prototype cost we adhered to now, while addressing insurance, is much further down the road. And finally, in order for a patient to wear the device and use it easily for assistance with daily activities, it must be portable. Since torque required to lift a load increases with distance from the pivot point, the more distal an object is, the harder it is to lift. So especially since patient weakness is a concern, the total weight of the device should be as light as possible, ideally less than a half kilogram distally, with heavier components located more proximally. Also, since mobility and independence are related, a patient should eventually be able to use the device at home in various situations, wearing it around the house without being chained to a static power source. The first orthosis I'll go over is OrthoHand Flex, the 3D printed grasping aid for flaccid patients.
Overall, I think that this is going to be an exceptional tool to manage stroke patients as they try and recover, because it's going to allow them to hold things in their hand that's been injured. And hopefully, as I get my strength back in that hand, it'll become even more of a tool for me to manage holding things and carrying things in a way that I never thought was possible.
That was a video of the prototype in operation. Now I will explain the details of design, testing, and analysis. The goal of this prototype was a customizable grasping aid to help flaccid neuro patients perform activities of daily living independently and reduce hands-on time for caregivers and therapists. The design criteria we focused on were easy to don and doff, soft and flexible, active grasping assistance for strength and activity performance, ability to provide therapeutic exercise, lightweight, low cost, and rapid custom sizing. We met all of these, as you will see shortly. The device is made from 3D printed TPU, similar to rubber, with foam padding and Velcro straps that leave the palm free to maintain contact sensation with the object grasp. It has this pneumatic tube in the bottom, you can see that pink tube coming out, and as air comes in to inflate the orthosis, the fingers curl away from the ridged side. You can see that in the figure D. Deflating makes the finger straighten. The 50th percentile male version weighs only 235 grams, about a half pound. And costs $27 to manufacture. The first step in automated custom sizing was to find ratio relationships between joint and bone positions to characterize the anatomy of the hand with a reduced parameter set in order to make custom design quick and easy. To do this, I plotted 5th to 95th percentile male hand data from a US military study for 6 key measurements. I checked each variable relative to each other variable and found the best fit lines intersecting the origin. Any ratio relationship with a correlation coefficient greater than 0.98 was considered a valid ratio. So the dependent variable could have its measurement eliminated and instead calculated based on the independent variable. You can see in these two sample plots, the top one shows measurements versus hand length. All the variables that correlate are plotted in color, and you can see that hand length is related to many other measurements. On the other hand, thumb breadth only correlates closely to a few measurements, and therefore it is not a good candidate to use as the independent variable. Doing this reduced the critical parameter set from 6 to 2 measurements, hand length and breadth. Well, it looks from the plot that using just hand length would be sufficient because it matches to all of the other variables. One caveat to note is that since this data came from a US military study, it is fit to American males. So by using both a length and a width measurement, we can accommodate other demographics better. Next, I designed a hand orthosis using variables based on these relationships. So the independent variables here are hand length and breadth, and all the other measurements are calculated from them. It is built using the open source platform Onshape, and parts regenerate without interferences for sizes ranging from 10th percentile female to 85th percentile male. We tested the prototype on a flaccid stroke survivor. For the first test, we wanted to see how quickly he could take it on and off, with a goal of less than a minute each. This subject's arm was completely limp, with just a little movement in the shoulder, and so he was not able to put the prototype on unassisted because his affected arm kept falling off the table. So we tested his caregiver doing it for him, and she was able to don and doff it in well under a minute each, much faster than any other published results. The subject was able to remove the orthosis completely by himself in under only 13 seconds. Next, we tested grasping functionality in several ways. First, we gave the subject several common objects to hold, one at a time, and pressurized the orthosis until he said he thought his grasp was firm. Then he shook his arm to verify stability, and none of the objects fell out. So we decided that that pressure must therefore be correct. The pressures required to hold various objects were all between 20 to 30 psi, shown in this table. Next, we tested grip force by pressurizing the orthosis so it curled around a hand dynamometer and recording the reading. The max force was 4.8 kilograms, or about 48 newtons at 65 psi, which was plenty compared to the stability testing, all between the 20 to 30 psi. Also, this is similar to human requirements for activities of daily living, and more than any published in literature for soft robotic hand orthoses. The final grasping test involved using the affected hand as a supporting task for two activities of daily living: slicing a fruit and opening and closing water bottles. The subject had not been able to do these activities since having his stroke, and that is why there is no control comparison, because he was not able to do them at all without the orthosis. But when he was wearing the orthosis, he was able to perform both tasks quickly and correctly. He cut 7 slices uniformly off the banana in a total of 10 seconds, and he opened and closed all 5 water bottles without spilling, in approximately 7 seconds per bottle. Now, no design project is complete without math, so I applied kinematics principles to model the interaction between a hand and an orthosis. I approximated the hand as a finger with a series of rigid links and revolute joints. And then I photographed someone wearing the orthosis at various internal pressures and used image processing in MATLAB to measure radius and angle of curvature, shown here in the picture with the angle of curvature is green and the radius of curvature is blue. From there, I was able to calculate joint angles, link angles, and confirm total range of motion. I did this for 3 situations. First, with the orthosis unloaded, no hand inside. Then with a small person's hand, and then with a large person's hand. The radius of curvature fit a 2-term exponential regardless of whether or not someone wore it. You can see that here, 2 terms, the A term and the C term, and then each of the exponents has a different term, B or D, related to the pressure. The angle of curvature increased linearly when unloaded and quadratically when loaded. So you can see that green one goes up linearly, and then the 2 blue ones are curved. And you can see that because of that, that means that even a limp hand provides some resistance. However, the total range of motion was close to our original goal of 250 degrees for the human hand. Now, the joint angles measured for both subjects on a second test fell reasonably close to the estimated values from the calculations. So these solid lines are the estimated values, and then the circles show from an experiment. You can see the MCP and DIP joints are similar. Those are your first knuckle and your last knuckle on your fingers. And then the PIP joint, which is your middle knuckle, is higher. Now, also as expected, the joints curl more tightly with increasing orthosis pressure. If a therapist wanted to target a specific joint or range of motion, they could use a chart like this to approximate the required pressure needed to get to that specific joint angle. The patient had very positive feedback regarding the OrthoHand Flex prototype. He was thrilled to be able to use his hand to perform activities he had not done in almost a year since his stroke, and kept exclaiming happily at each successful activity. Additionally, both the subject and the caregiver approved of the Velcro straps for ease of donning and doffing. The next orthosis I'll go over is OrthoHand Extend, the simple stretching aid for patients with spastic hands. First, we'll watch a video, and next I'll explain the details of design, testing, and analysis.
However,
just tell us if anything feels uncomfortable or too tight.
Run it for 1 minute now. Oh,
sure, yeah, I mean, if this is, if our feeling on it, it's comfortable. Also, yeah, it's about full. There are some people. Like when I started, I was one of most people, you know, I had no ability to just trying to retrain or create a path in my brain. Something like this is like whether you do it for 10 minutes or an hour or 2 hours, it would be interesting to see them help it kick in a lot quicker. Because they couldn't find any way to make it consistent.
Yeah, that's exactly what we're trying to get to. So if we can have a device, then all those studies can be done. What's needed in order to redo those pathways?
The goal of this orthosis is a simple stretching aid to help stiff neuro patients reduce spasticity and prevent contractures, and reduce hands-on time for caregivers and therapists. The design criteria we focused on are easy to don and doff, soft and flexible, ability to provide therapeutic stretching, lightweight, and low cost. Due to the structure and function of this device, custom sizing is not essential. We met all of these goals, as you will see shortly. Although the design of this device is very simple, it's essentially an inflatable bag with Velcro straps. We went through a lot of more complicated attempts before landing on this one. It starts out crumpled in the patient's fist. As in, air comes in, it inflates to gently open the patient's hand. Deflating allows the fingers to return to their equilibrium position. The bag is made of nylon coated in TPU and stitched through a commercial sealant to prevent leaks. This prototype weighs only 63 grams, an order of magnitude lower than any competing products, and costs about $5 to fabricate. We tested the prototype on 2 patients, one stroke survivor with medium hand stiffness and a traumatic brain injury patient with low hand stiffness. For the first test, we timed how quickly each person could don and doff the orthosis. Both were able to do this completely by themselves in record time compared to existing devices. For the cyclic stretching test, first we wanted to see what pressure would open the patient's hand comfortably and consistently. So we had each subject don the orthosis and slowly increase the air pressure until his hand opened. That pressure was then set as the desired peak pressure for the cyclic stretching test. Here's a block diagram of the testing setup. We have an air compressor sending airflow through a directional control valve to the orthosis, with pressure measured by an analog sensor. The system is powered by a DC power supply and controlled through Simulink real-time with a desktop computer. For the cyclic stretching test, the bag was inflated and deflated in a 4-second cycle, lasting a minute. Then the subject rested for 1 minute. This sequence repeated for a total of 5 sets. The results of an average of 10 cycles for the 1st and 5th sets are shown in these plots. You can see that pressure is essentially 0 until the bag fully inflates, at which point the pressure rapidly increases before the air supply is cut off and the pressure comes back down. Subject 1's curve in green peaks at 5 psi, because his hand was stiffer than subject 2, which peaks at 4 psi. The standard deviations are shown as gray bands. The consistency improved from the 1st to the 5th stretching session. You can see here that that's because of the change in the standard deviation that we know that. So that gray band is only visible on the first test. On the last test, it's barely visible at all, even though it actually is plotted. So the 5th stretching set was much more consistent than the first one. The mathematical modeling for this project was a joint effort between me and another grad student, Nitin Kumar. The goal was to calculate stiffness of the finger joints. This could help a therapist quantify patient progress over time, as stretching should relax the hand. So we do this by modeling the hand as a series of rigid links with stiffness and damping on revolute joints. And we use the constrained Lagrangian energy formulation to calculate joint stiffness given the change in angle as the hand opens. By photographing the hand in its equilibrium position and then in the stretched position, we can process the images to find change in finger angles. So start with the regular Lagrangian from the energy formulation. Then add length constraints connecting each center of mass to the next. Take partial derivative of these constraints with respect to each degree of freedom. Put them in matrix form to solve, where our internal forces include spring and damping, and the external forces include orthosis pressure times effective area. The offset here with alpha is because the surface of the inflated bag is curved, so the fingers never straighten beyond that surface. Gamma includes the constraint second derivatives and the desired second order dynamics to help the solution converge. In order to know if the stiffnesses we calculated were reasonable, we validated this approach using a mechanical hand. We made this artificial hand of 3D printed ABS links connected by revolute joints with torsion springs of known stiffnesses. It is naturally curved to mimic a spastic patient's hand so that it's naturally clenched, just like their hand would be. We arrange the springs from large to small, moving proximal to distal. So the stiffest springs are at the wrist, followed by the MCP joint, PIP, and DIP joints. The modeling achieved a close match for both the mechanical hand and the patient. So the black is a starting curled configuration. The blue is the final stretched configuration, and the red dashed line is what the simulation calculated. Here on the left are the mechanical hand results. Here we calculated joint positions based on known stiffnesses, and the match is close but not exact, with an error of about 4 degrees per joint. For the patient, the joint angles are known, and we calculated the stiffnesses. These are shown in the table to the left. It's important to note that these values will differ for every patient, and what is important is not the actual numerical value, but the relative stiffnesses across joints and across therapy visits in order to track patient progress in spasticity reduction. So if we measure these at the beginning, and they say a certain values, then ideally, as the patient is stretching their hand over and over, it loosens up and the stiffness is decreased. Both subjects had positive feedback regarding the orthosis and testing experience. They said that the device is something they use both at home and in public with no qualms, due to an eagerness to facilitate their recovery. Subject 1 was particularly enthusiastic, asserting that it was a fabulous stretching concept that could really open up possibilities, and that he would take any chance for improvement, needing to practice every day for results. Both subjects speculated on the potential benefits of the orthosis for improving quality of life, as less stiff hands could enable them to regain independence and efficiency with many activities. They specifically mentioned cooking, cleaning, eating, and opening water bottles as desired abilities that this device could hasten. Now I'll recap some of the highlights of these two devices. The hand orthosis prototypes are flexible, comfortable, sturdy, nearing or exceeding all primary design constraints, and solving issues with both existing technology and current research. The OrthoHand Flex design can be quickly and easily custom sized based on just 2 parameters, and is the first powered soft robotic hand orthosis to have this benefit. Its grip strength exceeds those of other soft robotic prototypes, and it enabled a stroke survivor to perform basic daily activities that had been previously unachievable. It weighs only 235 grams, costs $27 to manufacture for the 50th percentile male size, and is much faster to don and doff than any in published literature. The OrthoHand Extend Stretching Aid is simple and effective, weighing an order of magnitude less than any other research prototype and being twice as fast to don or doff by subjects completely independently. It is made of inexpensive fabric that can be crumpled in a fist, and it improves stretching consistency over just a few uses. The primary design constraints have been met. The initial evaluation of functionality was successful, and this work sets the stage for further prototype development, such as portability and controls, and evaluation of long-term effectiveness. First, I must thank God for his aid in resolving every single problem upon request. Whether it was hardware, software, or people-related, he came to the rescue every time. I should definitely have trusted more and not worried so much. And finally, also all those patients, caregivers, and providers who shared insights into their lives and struggles, and the ones who later participated in the research studies. This work would not have been possible without them. Next, I thank my committee for their various forms of support along the way. Dr. Eric Barth has been the most open-minded and flexible advisor I could ask for. He has been so encouraging, offered expert advice in many situations to improve the quality of my work, and kindly accommodated my atypical lab schedule. Dr. Tom Withrow, in particular, has mentored me since I first came to Vanderbilt nearly a decade ago, inspiring me to follow in his footsteps as a teacher. Dr. Carl Zelick has offered expert advice regarding human subjects in the IRB. Dr. Kevin Galloway has shared both the resources in the makerspace and his knowledge of soft robotics. And Dr. Ken Pence has been a staunch supporter for many years, always eager to offer an encouraging word. I really appreciate all of y'all's help. The other grad students in the lab have been pleasant and helpful coworkers, especially Charlie Galantine for his assistance with the uncooperative 3D printer, and Nitin Kumar for his mathematical modeling and simulation contribution. The National Science Foundation has funded this work, and several members of the Vanderbilt Wondery have helped me secure that funding and guided my customer discovery journey through the Ideator, Builder, and iCore programs. At MDSU, my department head, Dr. Ken Curry, has miraculously been able to consolidate my course schedule so that I could efficiently bilocate between schools. And his encouragement and appreciation show that he truly values me as both a human and an employee. John Roselle makes my life in the senior design lab so much easier, and my students keep life interesting. Thank you to those students who came out to watch this. I know this was not an extra credit opportunity, and so I really appreciate your support. And finally, I must thank my family for their unwavering prayers and support. They may not understand exactly what I'm doing and why this journey has taken so long, but they believe in me, and that is what matters. I'd also like to thank my fiance, Mel, for his constant encouragement, his willingness to try out many prototypes, and his copious feedback on what is too much of a hassle for a patient to deal with. Insights which have significantly improved the user-friendliness of the orthoses developed. Thank you for listening to my defense. What questions do you have?
That a lot of patients are like stiffly gripping, but you also notice that they can all put it on by themselves. I was just wondering how are they able to put it on by themselves with their hands like so.
Yes. Okay. So the question, I'm going to repeat these for the people on Zoom. So the question here is, how can the patient put it on himself if his hand is really tightly gripped? So a lot of patients are used to sort of like stretching out their fingers like this and smushing their hand flat down on a tabletop, or with a lot of these patients mostly did it just on their knee where they were sitting on a chair and they just smushed it open against their leg. So it's kind of a process of like peeling out the different fingers and smushing them down like that, which is something they do sometimes just to like relieve the tension in their hand, but that's the approach that they took for putting these on. And that's sort of how why we designed it to be something that was like easily crumpleable, so that they could just kind of like shove it in however it got there. And then as the air comes in, everything will all kind of straighten out. Yes.
Can you maybe talk about the choice of having a single actuator as opposed to a lot of the other designs tend to actually be stronger? Like what was your conceptual design diagram when you were choosing What made you go just a single actuator as opposed to multiple?
Ye- Yes. Okay. So that's a good question about single actuator versus other ones. And I'll just go to the screen so that y'all can see. Like pretty much all of the other ones look like gloves and have the individual finger components. And from us talking to people, because they can't move each of their fingers, and a lot of times, like as they were peeling out, as they're trying to put something on their hand, they get one finger out. And then as they're trying to get their second finger out, the first one comes back in. So they explain that like trying to get anything on individual fingers is just way too much of a hassle. So we just kind of went for the basic thing. And also because of what most people told us is their functionality they needed was gross motor as opposed to fine motor, then kind of having all your fingers together, you can still kind of basically hold stuff.
And I was just, there was a slide where they were solving for the given shape, you know, for a given impression.
Okay, yes, let me find that one. Okay, I think it was this one. Is it? Oh, okay, yeah, the other one.
Yeah, so, I guess the one thing that was not clear to me was what goes into a red line here. It was not clear to me what went into a red line. You know, you don't really have you have some from some other initial parameters for human hand. Did you include like kinetic energy or was it just plastic energy?
No, it was basically just the elastic energy. So we didn't have a way to measure velocity. And also the stretching was so slow that we kind of assumed that velocity is essentially negligible, or at least in the acceleration too. So we just used basically, yes, just the elastic energy.
Okay, so you have an underactive system, right? So you potentially have infinite solutions for the given shape. How did you convince your optimizer to converge to a shape? Was it just kind of tuning the coefficients in the weights?
So we started out with just giving it some basic initial guesses, and then we had it in a for loop where we solved iteratively each time, and we kind of had an error term that sort of like if it would save the closest possible solution, the one with the lowest error, and then we actually had like a random number generator in there that it would just like knock all the parameters out a little bit and see if it could find like basically another local minimum. Yeah, to kind of optimize it that way. Yeah, Eli.
You mentioned applications for Parkinson's. What sort of considerations were taken into account when thinking about like tremors?
Yes. Okay. So he asked about Parkinson's disease. That's a really good point. So one of the things that we found through talking to people is that Parkinson's patients are actually not good candidates for bracing. And that's because it actually strengthens their tremors. So what the therapist told us is if you have something that constrains the Parkinson's patient's hand, his whole arm will just start to shake. It's not like, yeah, that disease really like connects to the brain effects of that disease to the body are different than some of the other types of patients. So they wouldn't be a good candidate for things like this. Yes.
So as you consider the pathway to commercialization, I mean, right now you're tethered to compressed air, right? So as you develop and that product, what's the solution for everyday life?
Okay, that's a good question. So there's actually another student in my lab, Charlie, who is working on a self-contained pump. So it's a bidirectional pump, and I think I have some slides on it I can show you. But basically that would mount higher up on the patient's arm, and it would be able to cycle fluid in and out without needing an accumulator. I'll show. Okay, this is okay. So this is his pump design, and it's pretty small. I think it's like maybe 3 or 2.5 centimeters. It's like only this big. So it's really small and lightweight. And the 3D printed version is also pretty cheap to manufacture. So we would just be able to connect, I don't have them anymore, but that air tube that comes out of the bottom of the orthosis, just hook it up to the pump. Daniel?
Oh, what plans do you have to market these products to consumers? And what kind of time frame are we looking at before they're available to whoever wants to buy them?
Okay, so question about when are people going to actually take these home? So one of the things I learned through the iCore program is that starting your own business is a hassle. So ideally, I would like to progress this project further, get a patent, and then kind of sell the rights of that patent to a company who already makes the devices that are similar to this, that already exist, that because patients are used to getting them through that channel. And I think that would be the easiest route to reach patients. So there's no specific timeline on that. As always, research is dependent on the funding, and the only thing certain in this economy is inflation. So we need to get some grants, have another student would step in, kind of take the pump that Charlie has and then take the hand part that I have and kind of integrate those together in order to get it like more of a product. Yes.
Do you anticipate that you would have to do more trials in order to really get it to that next level so that you could have occupational therapists kind of buying into this on a more regular basis?
Yes, that is a good point. So in order for anything to get FDA approved, there's actually a very rigorous process of human testing that you have to go through and like different levels of device. So it would need to be tested on a much larger scale than we tested it on these patients. So after we get it to like a more self-contained level, then we'd have to do more of a long-term study on large groups of people, which is kind of not so much in the engineering, like on the engineering side of things, it's like on the medical side of things, and just have people test it before it would be FDA approved for commercial sale, or especially for insurance. That.
The use of Velcro straps, was there ever any concern of cutting off circulation? Was that ever considered, or did it ever happen?
Okay, so that's a good question. He asked about could the Velcro straps cut off circulation? So the Velcro actually, like, if the pressure gets too big, the Velcro can actually pop off. But there was one subject in a second test that we did that wasn't shown here. We just kind of had it pressurize his hand for longer and just over and over. And about 11 minutes of like constant, he complained that the stitching on the straps was starting to hurt his fingers. So it wasn't the pressure wasn't really a concern, but the straps do need to be a little bit better. And we were very careful with turning up the pressure slowly and watching the patient, asking them, did it hurt? So that we would be able to intervene in the case that something did happen, but fortunately nothing did.
All right, if there aren't any other questions, let's thank Alyssa once again. Congratulations.